In the design of rotor, in last lecture we have seen estimation of length of air gap between stator and rotor. The factors affecting the length of air gap and the effect of length of air gap on the performance of three-phase induction motor. Now, as far as rotor construction is concerned, there are two types of rotors used in induction motor. Number one is squirrel cage rotor, and second is the wound rotor or slip ring type motor. So in the design of rotor, we have to select number of slots. While selecting the number of slots in the stator of three-phase induction motors, there are some guidelines that we have to follow. In the design of rotor slots, we have to follow some guidelines. The rules or guidelines for selecting rotor slots. Guideline number 1. Stator slots should not be equal to rotor slot. That is, stator slot SS should not be equal to rotor slot SR. The rotor slots SR should be 15 to 30% smaller or greater than stator slots. Greater than stator slot SS. This is guideline number 1. Stator slot should not be equal to rotor slot, and rotor slot should be 15 to 30% smaller or greater than the stator slot. Guideline number 2. Difference between stator and rotor slots. SS stator slot minus SR rotor slot. So difference between stator slot and rotor slot should not be equal to P, where P the number of pole should not be equal to P, 2P or 5P to avoid synchronous torque. Synchronous torque developed in the rotor due to the harmonics present in the air gap. This is guideline number 2. Guideline number 3. So difference between stator slot and rotor slot should not be equal to 3P to avoid the magnetic locking. So difference between stator slot SS and rotor slot SR should not be equal to 3P, P the number of pole, to avoid the magnetic locking between stator and rotor. So if there is magnetic locking, then rotor refuses to start. So difference between stator slots and rotor slot should not be equal to 3P. Guideline number 4. Difference between stator slot and rotor slot should not be equal to difference between stator slot and rotor slot should not be equal to 1, 2, p plus minus 1 or p plus minus 2 to avoid noise and the vibrations. Noise and vibration. So these are the 4 guidelines we have to follow while selecting the rotor slots. Or as a summary, we can see from the above guidelines, summary of above guidelines. So difference between stator slots and rotor slot SR should not be equal to 0 plus minus P plus minus 2P plus minus 3P plus minus 5P plus minus 1 plus minus 2 plus minus P plus minus 1 plus minus P plus minus 2. So these are the guidelines we have to follow, and this is the summary of these guidelines we have to follow while selecting the rotor slots. Now reduction of harmonic torque. As we know, flux in the air gap is not pure sinusoidal or perfect sinusoidal. The flux in the air gap have some harmonic field. The harmonic field in the air gap is due to the windings, due to slotting, due to saturation of magnetic circuit, and due to non-uniform air gap. Due to this harmonic field in the air gap, harmonic EMF, harmonic current, and the harmonic torque develop in the rotor of the three-phase induction motor. We have to nullify or we have to reduce this harmonic torque developed in the motor. Otherwise, there is some disadvantage or bad effect on the motor performance. There are some methods adopted to determine the harmonic torques. The reduction of harmonic torque. Harmonic torques. How to reduce the harmonic torques? The number 1 methods. These are the 4 methods. Number 1 method is cording of winding. Method number 2 is integral slot winding. Integral slot winding. Method number 3 is skewing of rotor slot. Skewing of rotor slots. And number 4 is increase in air gap length. Increase in air gap length. Using these 4 methods, we can reduce the harmonic torque developed. Now considering above 4 methods one by one. Method number 1 is chording. To eliminate harmonic torque, torques, stator winding, the stator winding corded with integral value of QS, where QS is slots per pole per phase. This should be winding corded with integral value of slots per pole per phase. Method number 2 is integral slot winding. The fractional slot winding should be avoided. And the integral slot winding should be used. Integral slot winding should be used. So we have to use integral slot winding to eliminate the harmonic torque. Factor number 3, skewing. Method number 3 is skewing. Motor noise, vibrations, and cogging can be entirely eliminated by skewing either stator or rotor slots. The stator or rotor slots, either stator or rotor slots are skewed, but generally rotor slots are skewed. Then harmonics will be reduced and it produces the uniform torque and less noise. Let n the order of harmonics. Then np will be the number of harmonic poles. This is angle between adjacent harmonic pole. Angle between adjacent harmonic pole. So this is, we can say, harmonic pole pitch. Angle between adjacent harmonic pole. This is 360 degree upon number of harmonic pole. This is mechanical angle. For elimination of nth order harmonics, nth order harmonic angle of skew theta sk, angle of skew theta sk, this is 720 degree upon NP, mechanical degree. This is angle of skew in mechanical degree. But angle of skew, electrical angle of skew, electrical angle of skew theta sk in electrical, this is equal to P by 2 theta sk mechanical, theta sk mechanical. So this is P by 2 theta sk mechanical 720 upon NP. This is equal to 360 degree upon N. This is electrical angle, electrical degree. So this is theta sk in electrical 360 upon N. But theta 360 is nothing but 2 pi. Therefore theta sk, this is equal to 2 pi upon N. This is in electrical radians. The rotor conductor skewed over theta sk. Rotor conductors are skewed over the angle of skew theta sk. So EMF induced in the rotor depend on distribution factor, because EMF induced is depend on winding factor, and winding factor is coil span factor into distribution factor. So EMF induced is depend on the distribution factor. EMF induced in rotor depend on distribution factor, winding distribution factor, this is kWr, and this is distribution factor is kd1, distribution factor sine of theta sk upon 2 upon theta sk upon 2. This is for fundamental flux, for fundamental flux waveform. Now for distribution factor for harmonic flux, this is equal to sine n theta sk upon 2 upon n theta sk upon 2. This is for nth order harmonics, nth order harmonics. But we have seen theta sk is equal to 2 pi upon n. So substitute. So if we substitute, theta sk is equal to 2 pi upon n in above formula. This is kdn is equal to sine of n theta sk 2 pi upon n into 2 upon n into 2 pi upon n into 2. If we simplify this, this is 0. So from above it is clear that distribution factor for nth order harmonics is 0, and as EMF induced in the rotor is directly proportional to the distribution factor, it is depend on distribution factor. So distribution factor is 0, therefore harmonic EMF induced in the rotor winding is 0, so that no harmonic current developed, and so that we can say no harmonic torque is developed. Therefore we can see, so harmonic torque is totally eliminated. So from above it is clear that harmonic torque is completely nullified, completely eliminated. But usual practice is to skew the rotor, is to skew the rotor equal to 1 stator slot pitch, stator slot pitch. So theta sk is equal to pi d upon ss. This is stator slot pitch in terms of periphery. In terms of angle, theta sk is 360 degree mechanical upon stator slot. This is equal to 2 pi upon ss in radian. So theta sk mechanical is equal to 360 degree upon ss. This is mechanical degree. Theta sk electrical is equal to p by 2 theta sk mechanical. So this is p by 2 theta sk mechanical is equal to 2 pi upon ss. This is pi p upon ss. This is in radian, electrical radian. This theta sk in electrical radian. But the order of slot harmonics is slot harmonic n order of slot harmonics n is equal to 2 stator slots per pole plus minus 1. This is the formula. Order of slot harmonics n is equal to 2 slots per pole plus minus 1. So distribution factor for slot harmonics this is equal to kdn sin n theta sk upon 2 upon n theta sk upon 2. So substitute n and theta sk in this formula. This is equal to sin n is 2 s per pole plus minus 1. This is n into theta sk pi p upon pi p upon 2 ss upon n is 2 ss upon p plus minus 1 into pi p upon 2 ss. So if we simplify this thing, we get plus minus sine pi p upon 2 ss upon pi plus minus pi p upon 2 ss. Now consider induction motor having 4 poles and 36 slots, stator slots. Now for this, the order of slot harmonics is slot harmonics. This is equal to formula n is equal to 2 ss upon p plus minus 1. If we put p is equal to 4 and ss is equal to 36 in the formula, we get order of harmonics. This is equal to 19 and 17. This is higher order harmonics, this is lower order harmonics. So this is positive sequence harmonics, this is negative sequence harmonics. For this distribution factor for slot harmonics, for slot harmonics, this is KD19. This is equal to minus sine pi into 4 upon 2 into 36 upon pi plus pi into 4 upon 2 into 2 into 36. This is equal to minus 0.052. And for lower order harmonics and for 17th order harmonics, distribution factor KD7 is, if we calculate this way, we get this is equal to 0.058. So from this it is clear that the value of distribution factor, this is 0.058, this is 0.058 and this is 0.052. So this is reduced, so that we can say कि harmonic EMF induced in the rotor winding is reduced, so that harmonic current developed in the rotor winding is reduced and the harmonic torque is reduced. The skewing the rotor slot for the skewing decreases the winding factor for the fundamental and therefore the increase the leakage flux of the motor. Therefore, it lowers the power factor and the overload capacity of the machine. So now this is torque speed characteristics. This is speed, this is torque speed characteristics. So this is the torque speed characteristic, this is torque speed characteristic, this is speed, synchronous speed. This is torque speed characteristics with skew and without skew. So this is the torque speed characteristics with skew, and this is the torque speed characteristics without skew. So this is with skew, and this is without skew. From the characteristics, it is clear that without skewing the rotor, starting torque getting is more. At the same time, maximum torque is also getting more. Point number 4 is increase in length of air gap. This is one of the method to reduce the harmonic torque. Method number 4, increase in air gap length. If the length of air gap increases, then harmonic flux decreases and harmonic torque decreases. But if length of air gap increases, no load current increases, and so that power factor of the motor decreases. So as length of air gap LG increases comparatively, then harmonic torque decreases. Harmonic torque decreases. But as LG increases, but no load current increases. So power factor decreases. Now cross-sectional area of rotor bars. Area of rotor bars. The induction motor performance depend on rotor resistance. Performance of motor depend on rotor resistance. So if rotor resistance is comparatively large, high rotor resistance, its starting torque is increasing. Starting torque TST is increasing. But disadvantage is that I square R loss in motor is also increasing, so that efficiency of the motor is decreasing, and at the same time there is overheating of the rotor. So value of rotor resistance depend on the current density selected for the same value of current. So if higher current density, rotor resistance R2, rotor resistance depend on current density in rotor, this is del R. So if higher value of current density is selected, if del R selected large, then area of rotor bar decreases. Therefore rotor resistance resistance increases. Rotor resistance increases. Therefore, starting torque of the motor increases. But I square R loss in the rotor increases and efficiency of the motor decreases. Generally, rotor resistance is resistance of bar resistance plus end ring resistance. Bar resistance plus end ring resistance. Current density in the rotor bars del R is generally selected between the range 4 to 7 ampere per mm square. Any value between this you can select it for the calculation of this. Then area of each bar, this is AB, this is current in bar, each bar upon del R, this is mm square. So current density is ampere per mm square. This way you can calculate. So first calculate current in rotor, current in bar, then select suitable value of current density in the rotor. Bar current is divided by the del R, we get size of each bar in mm square. Next point is shape and size of rotor bars. Shape and size of rotor bars. Rotor slots used either closed or semi-enclosed type. Rotor slots are closed type slots or semi-enclosed type slot. Semi-enclosed type. Closed slots, semi-enclosed type slots. So this is semi-enclosed type. This is surface of the rotor, circular slot. Then these are the semi-enclosed type slot, and this is closed slot. This is closed slot, and this is the closed slot. This is closed slot. This is the surface of rotor. Surface is smooth, and here is the small slot opening. This influences the length of air gap. Generally, closed type slots are generally used for small rating machines because reluctance of the air gap is small because of absence of slot opening. So therefore magnetizing current required is small, and as the surface of rotor is smooth, the operation of machine is quieter, less noise is produced. But disadvantage is that the leakage reactance with closed slot is large. Therefore starting current is controlled, and therefore but the overload capacity of the motor is small. But if semi-enclosed type slots, because of reluctance more, leakage reactance comparatively small, so if you used semi-enclosed type slot, this machine gives the better overload capacity. Next point is rotor slot insulation. Rotor slot insulation. No insulation is used between rotor bars and rotor core. Small clearance about 0.15 to 0.4 mm is kept between the rotor bars and the core depending on the slots, whether slots are skewed or not. So no insulation between rotor bars and slots. A clearance of 0.15 to 0.4 mm is made between rotor bars and the slot.